We're going to talk about rooted trees in this video. And a rooted tree is a directed tree with a particular vertex labeled as the root, such that for every other vertex there is a directed path from the root to that vertex. Now, not all directed trees are rooted trees, even though perhaps you might say, well, can I choose an arbitrary vertex to be the root? The following theorem is more specific. It says a directed tree is representable as a rooted tree if and only if one vertex has n degree 0 and all other vertices have n degree 1. So that's pretty specific. So a rooted tree is a special kind of directed tree. Now when we draw a rooted tree, we do not usually put arrows on the edges, even though it is a directed tree. That's because the direction is understood. All the edges from the root are out edges, and then for the remaining edges, there is one edge that is in, and all of the rest are out. And the incoming edge is coming from the root, or a path from the root. And since all of this is understood, we frequently do not put the arrows there. Now you've come across a rooted tree before, because in our exercise where we wanted to construct a tree, it showed all possible paths from the pizzeria to the grocery store. So what we did is we had the pizzeria as our root, and then we had directions added that were implied. So we're going to look at rooted trees more formally now. So rooted trees have what we call levels, and we start with level 0. So the root vertex is at level 0. Then the distance from the root determines the level of each vertex. So all of the vertices that are distance 1 from the root are at level 1. And all of the vertices then that are distance 2 from the root are level 2, and so forth. The longest path from the root is the height of the rooted tree. So, since each vertex has n degree 1, we say that the vertex from which that n degree is coming is the parent of that vertex. And then all the other edges are out degrees, so all of its out neighbors are its children. In particular, let's say we look at vertex U in a rooted tree. Then the vertex above it is the parent, and that is its n degree 1. And then all the vertices at the next lower level that are its neighbors are called the children of U. Sometimes the children of the same parent are called siblings. Every vertex of degree 1 is called a leaf node. That is, all the vertices that have no children are leaves. And all the other vertices that are not leaves are called internal. A binary tree is an example of a rooted tree. A binary tree is a rooted tree in which each vertex has 2 or fewer children. And binary trees are used extensively in theoretical computer science. Now, it doesn't have to be binary. We could say M-ary for any M. So the generalized definition is an M-ary tree is a rooted tree in which every vertex has M or fewer children. Proposition 3.2.2 says an M-ary tree has at most M to the K vertices at level K. And the proof is by induction. It's easy and straightforward. You'd like to anchor your proof if K is 0. M to the 0 would be 1, and we have just one vertex at level 0, and that's the root. And then if you assume for a fixed K that there are at most M to the K vertices, then it is straightforward to argue that at the next level, you have M to the K plus 1 at most, M to the K plus 1 vertices. Now, not all isomorphic trees are necessarily isomorphic as a rooted tree. That is, you could have two trees that are isomorphic, but if the isomorphism does not map a root to a root, then we do not say that they're isomorphic rooted trees. So it's possible to have two trees that are isomorphic but have different roots. So in that case, they would not be rooted isomorphic trees. So we're going to continue our discussion on binary trees next week, and this concludes video 3.